Hello everyone, this is chapter 6.2 and in this lecture we'll be considering the other half of nucleophilic substitution reactions, that's SN1. This lecture will consist of 4 videos, the first of which is just a general overview of SN1 nucleophilic substitution. Video 2 will look at the factors that affect the rate of reaction for this, and this will include the leaving group and also looking at the topic of carbocation stability. In video 3 we will extend this carbocation stability to include those that have resonance stabilisation, which also introduces another element into this reaction, which are regiochemical outcomes. And lastly we'll look at the second factor which affects the rate of SN1 reactions, and these are the solvent effects. So let's get started. A second model for the nucleophilic substitution reaction is called the SN1 mechanism, and the 1 in SN1 indicates that the rate determining step of the reaction is unimolecular. In other words, the rate determining step involves a single molecule breaking apart rather than the 2 molecules colliding, as was the case in the SN2 mechanism. So in effect this reaction happens over typically 2 steps, and there is sometimes a third step which is a deprotonation step. So how do we know that this process is unimolecular? Well, one of the things that we can look to is the rate expression for this reaction, just like we did for the SN2 reaction. Here we have a solvolysis reaction occurring between tert-butyl bromide, which is an alkyl halide substrate, and the alcohol. So the alcohol here is ethanol, and this is our nucleophile. If we measure the rate of reaction at constant ethanol concentration and at a constant temperature, but increase the concentration of tert-butyl bromide, we can see that there's a directly proportional relationship between the rate and the increase in tert-butyl bromide concentration. However, if the same experiment is repeated, except this time we change the concentration of the ethanol to increasing concentrations at a constant concentration of tert-butyl bromide and a constant temperature, we can see that this has 0 order rate kinetics, which means then that the process only involves the tert-butyl bromide. And this means then that this is the rate determining step of the reaction, and that things occur in 2 parts. Let's have a look at what these 2 parts are now. Here is the rate determining step for an SN1 reaction, and the first step requires the heterolytic cleavage of the carbon X bond, where X is typically a halide. And because no other bonds are being formed in this step, this is a particularly endothermic process and has a high energy of activation, and we'll see this in the free energy diagrams. The fact that the halide departs at all is largely because of the ionizing ability of the solvent that you use. So we'll be talking about the solvent effects in a different video. We should also note that this reaction is in equilibrium, and the moment that the planar carbocation is formed, we have then the opportunity for that halide that was displaced to go back and react with that empty p orbital. We have essentially got a nucleophile and an electrophile, and that carbocation is particularly electrophilic because it has the incomplete octet. The next step in the SN2 reaction is a fast step, and this involves using typically the lone pair of a weak nucleophile, and this is usually the solvent, so it might be water, it could be ethanol or methanol for example, and that lone pair acts as a Lewis base or a nucleophile, donating its electron pair to the carbocation, which is extremely electrophilic, and this is what gives the cationic carbon its 8 electrons, and so this reaction happens very, very quickly. There is also a third step possible in this process, and we'll talk about this step a little later. So we're back to cats again, and here we can see a different story from what we looked at when considering the SN2 mechanism. This story only involves the grey cat, Let's have a look at this now in terms of the reaction coordinate. I've added a couple of extra pictures here to represent more accurately the cat bed scenario. So before we have our starting materials, so we have our alkyl halide and our nucleophile, just like in the SN2 example. Except this time, the free energy of activation requires the breaking of the bond. And this is represented more accurately as the grey cat is leaving its bed. So this is actually a transition state. Now the energy minimum that we see is called an intermediate, and this is something that is isolable in the same way that the empty cat bed is something that could be isolated. And this is essentially what has happened, is that the grey cat has left its bed. Now we have a fast step in that the nucleophile approaches the bed, and the nucleophile being the ginger cat, of course, and this still requires a small amount of energy, but the bond forming process then results in products that are once again lower in energy. However, let's be serious here and talk about a genuine example of a reaction that does involve the third step. Hydrolysis is the term that you will frequently encounter both in organic and biological chemistry. And hydrolysis just means breaking with water. So in a hydrolysis reaction, a water molecule or a hydroxide ion participates in the breaking of a covalent bond. Solvolysis is just simply a more general term used when a bond in a reagent is broken by a solvent molecule. In this case, the solvent is water. But in other cases where we use weak nucleophiles, this could be an alcohol, such as methanol or ethanol. Here we see the reaction coordinate for a typical solvolysis reaction, and there are two intermediates. Each of the two positively charged intermediates, this is the tert-butyl carbocation and also the tert-butyl oxonium ion, sit in a mini valley in the path of the reaction. And these are both higher in energy than both the reactant and the product, but they are lower in energy than any of their previous transition states. So the first bond breaking step is the slowest, as this has the highest activation energy, and this leads to the highest energy species, so the carbocation intermediate. Step 2 is rapid because a new covalent bond is formed between the carbocation and the water molecule, and no covalent bonds are broken. And then finally, the Bronsted-Lowry proton transfer that happens in step 3 are rapid. Both of these two steps are fast steps because they have low activation energies. Let's focus now on the intermediate, that is the carbocation. Firstly, the geometry of these carbocations are all trigonal planar, and this means that they have bond angles of 120 degrees. So the central carbon atom in a carbocation is electron deficient, and so it only has 6 electrons in its valence shell. The hybridization accordingly then is that it is sp2 hybridized. This vacant p orbital of the carbocation contains no electrons, but it can accept and does accept an electron pair when the carbocation undergoes further reaction. Here we have a chiral substrate undergoing an SN1 reaction. See if you can work out the configuration of the stereocenter in substrate A. Pause the video and resume when you have an answer. Okay, so substrate A has an S stereocenter. However, once the heterolytic bond cleavage has occurred, we form the planar carbocation. And this means that the incoming nucleophile can either attack from the left or it can attack from the right. Now see if you can work out the configuration of each of the products. We can assume that the nucleophile is always going to have priority 1. Pause the video and resume when you have an answer. Okay, so what you should have is for the top enantiomer is R, and for the bottom enantiomer we'll have S. And what this is an example of is a 50-50 racemic mixture. There is no preference for attack from either side for this particular reaction. One of the things that is possible to do is to measure the optical activity. So we may start with a chiral substrate that rotates plane polarized light to the right. Remember, this has nothing to do with R and S, but when we make the measurement after an SN1 reaction, because there was an equal probability of the chiral center having an inversion of configuration and 50% of it retained its configuration, then we now have an optical activity that has 50% of which that will rotate plane polarized light to the right, and 50% of that mixture will rotate plane polarized light to the left. And so what happens is we end up with a 0 optical activity reading.
This concludes part A.
In this video we're going to have a recap of leaving groups and talk about the structural features that stabilize carbocations. So the pattern for leaving groups is the same for SN1 as it is for SN2. In other words, if we look at the conjugate acid of our leaving groups, then the pKa values give us some indication as to how these are able to stabilize a negative charge, or in the case of water, it forms a neutral molecule, so it has a pKa that's -1.7. For anions such as the halides, the size of the anion is important, and with respect to any base that can be resonance stabilized, then this also is a factor that can be taken into account. Now let's have a look at the carbocations in more detail. The substrate in an SN1 reaction also determines the rate of reaction, and this is directly related to how stabilized the carbocation can be. With increasing numbers of alkyl groups, so moving from methyl all the way up to tertiary substrates, we can see that the methyl carbocation is the least stable and that the tertiary carbocation is the most stable. The reason for this stability can be explained on the basis of hyperconjugation. On the right hand side we see a diagram that shows the electron delocalization via partial orbital overlap from a filled bonding orbital. This happens to be a carbon-hydrogen for a secondary substrate into the adjacent unfilled orbital. In the case of this carbocation, the unfilled orbital is the vacant p orbital of the carbocation, and the filled orbitals are carbon-hydrogen bonds. They can also be carbon-carbon sigma bonds at the carbons that are adjacent to the p orbital for the carbocation. Sharing of this electron density from either adjacent carbon-hydrogen or carbon-carbon sigma bonds with the carbocation p orbital delocalizes the positive charge, and we can see this in the electrostatic potential map for different carbocations. The high region of positive charge is localized on our methyl cation, and so this is not very stabilized. Anything that can cause the positive charge to be dispersed or delocalized, either through hyperconjugation, inductive effects, or resonance, causes a system to be stabilized. And we can see that this region of blue decreases with the increase in alkyl substituents. Here we see the reaction coordinate for the SN1 reaction involving the formation of the methyl carbocation all the way to the tertiary carbocation. And the activation energy is so high for the methyl carbocation that the rate simply isn't able to be measured. In other words, this reaction simply doesn't take place. For the primary carbocation, of course, we see a reduction in the activation energy, but it's still pretty high, and the rate is only 1. So that doesn't make it good. It just means that relative to this, there are better substrates for SN1 nucleophilic substitution. If we go to a secondary carbocation, we can see that, yes, again, the activation energy is lowered, but the rate only increases 12-fold. But when we go to a tertiary carbocation, the activation energy now being the lowest, we can see that there's a 1,000,000-fold increase in the rate compared to the primary carbocation that's formed. And this is significant and tells us that tertiary carbocations are the ones that are the most likely to take part in an SN1 nucleophilic substitution.
This concludes part B.
And in this video we're going to continue to discuss the ways in which the carbocations can be stabilised. And this requires a small focus on the use of resonance stabilisation. If you remember, stabilisation of a carbocation can also occur through resonance effects. So a positive charge is stabilised when it's delocalised over more than one atom. And here we have an allylic carbocation. And the allylic carbocation is where the positive charge of the charged carbon is adjacent to a double bond. And this can be resonance stabilised as seen here. Here we see two sets of resonance stabilised carbocations, both of which have allylic centres. See if you can work out which set of resonance structures are more stable and which set are less stable. Pause the video and resume when you have an answer. So the resonance structures on the left hand side have the positive charge delocalised over two secondary carbons. And now these are going to be less stable. And the reason for this is because the structures on the right hand side, one of these structures, this is the left structure, has the charge delocalised over a secondary carbon, but the other structure has the charge delocalised over a tertiary carbon. And so on the whole, these two resonance structures are more stable than the other pair of resonance structures. Here's another example of an allylic substrate. So if the bromine dissociates, then the positive charge that remains can be resonance stabilised, and this will lead to two different carbocations. So just as there is choice for attack from the top or the bottom, and this will dictate the stereochemistry, there's now also a choice for the location that water molecule can attack these carbocations. And this is called the regiochemistry of the reaction. So if it were to attack the primary carbocation, then we would form an achiral product as seen by the red pathway. But if it attacks the blue route, we can see that the secondary carbocation, which is really the allylic position, the water then can either attack from the top or the bottom. And the wavy line just indicates that there are two possible enantiomers here. Either the water attack from the top, which is indicated by the top product, or the water attack from underneath, which is indicated by the second enantiomer. And this gives the racemic mixture. Just as the allylic position is able to resonance stabilize, the benzylic position is also capable of resonance stabilization. So the benzylic carbon is the carbon that is attached to the benzene ring, and this carbon has a leaving group, it's the bromine. Should this bromine leave, then we would have a carbocation on the benzylic carbon. And this can be highly resonance stabilized as seen by the number of resonance structures drawn for this particular molecule.
A rose by no other name would smell as sweet. But what causes that sweet smell? Well, it's SN1 substitution. Geranyl diphosphate or pyrophosphate, the pyrophosphate group is shown here, is converted to geraniol, which is the fragrance that is responsible for the smell that's found in roses and is used often in perfumery. So initially there's a dissociation of the pyrophosphate ion, and this gives a stable allylic carbocation, which then goes on to react with a water nucleophile and then transfers a proton to yield geraniol. And this all happens via an SN1 mechanism.
This concludes part C.
And in this video we're going to look at the use of polar protic solvents for SN1 nucleophilic substitution reactions. So a polar protic solvent is capable of forming a hydrogen bond, And we can see this here because the sodium ion is both solvated by the ion dipole interactions with water, and bromide ions are also solvated by hydrogen bonding with water. And what this shows is a solvent cage surrounding both of these anions. Let's now relate this to an organic context. So a protic solvent has at least one hydrogen atom that is capable of participating in a hydrogen bond. And here we have the protic solvent ethanol, and this facilitates the formation of the carbocation by forming hydrogen bonds with the leaving group as it departs. This lowers the energy of the transition state that leads to the carbocation. In addition to this, it also solvates the carbocation and stabilizes this. Now, water is the most effective solvent for promoting such an ionization, but of course most organic compounds do not dissolve appreciably in water, but they do dissolve, however, in alcohols, and quite often mixed solvents are used. So methanol water and ethanol water are two common mixed solvents for nucleophilic substitution reactions. The transition state for the heterolytic cleavage of the carbon-bromine bond is shown, and the carbon-bromine bond is somewhat polar in the starting material, and it's even more polar in the transition state, and the products are completely ionic. Polar protic solvents have large dipole moments, and so they lower the energy of both the transition state and also the starting material. But they stabilize the transition state more because it's polar, and this in turn lowers the activation energy, and so the reaction goes faster.
This concludes Part D.